go. So infinite limit, right? A limit in which f of x increases or decreases without bound is called an infinite limit. So that's kind of the focus of this final little section here. So the notation here is, as noted, it looks pretty normal, right? The only thing that's abnormal about this is the fact that it's equals infinity or equals negative infinity, right? But the limit as x goes to c of f of x. That's all the stuff we've been talking about. Can we talk about what it does not mean first? It does not mean this. It does not mean that the point c comma infinity is on the graph. Because if the point c comma infinity was on the graph, what does that imply? It's not infinity anymore, right? Because we got there, right? We got there. We said, hey, I've arrived, c comma infinity. It's right there. That means you've done what no one else could do. You counted to infinity. You're obviously well beyond all of us. I don't think it's possible, right? C comma infinity is not on the graph. So that's what it does not mean. What it actually does mean is that what we said before, really, f of x is increasing or decreasing without bound. You can kind of see it peeking out from the bottom of the notes on the screen there. You can see it on the bottom of your notes. You can see, you got a couple of graphs there that, the one on the left, you can see, as we get closer and closer to, it looks like 1, it looks like we're increasing without bound. On the right, kind of a sort of a similar pattern. What do you see, what's the commonality? What is associated with both of those graphs? Vertical asymptote, right, yeah. So whenever you have an infinite limit, that's almost always going to mean that you've got a vertical asymptote somewhere, around what we're looking at. So I'll just put VA right here, indicating that, hey, what it really means, what it does mean is that you've got a vertical asymptote somewhere around where you're looking at this limit, okay? Could also be a slant asymptote, I suppose, but we're gonna pretty much always be looking only at vertical asymptotes in our class. So why don't you take a look at those two graphs, and I want to just do a couple of little examples with those. I just want to run a couple of examples by you. So let's take a look at the one on the left, just the graph on the left only. I'm going to say limit, we'll call this question A, limit as x goes to 1 from the left of f of x. Limit as x goes to 1 from the left of f of x. What would you say the answer to that is, just based on looking at the graph? As you get closer and closer to 1 from the left side, what are the y values doing? Increasing without bound, also known as infinity, right? You can see as we get closer to that vertical asymptote, the graph will just keep going up, up, up. And so I'd say saying infinity here is a good description, right? We're saying that the graph is increasing without bound. Question B. What if I said limit as x goes to 1 from the right of f of x? Again, looking at the graph over there on the left side. What would you guys say to that one? From the right. It would be infinity again. Yeah, good. And then finally I could ask the other question, limit as x goes to 1 without any directional stuff. What would you say there? So you could say D and E. In fact, we would have said that in that other section, right? In section like 1.3, I think it was, maybe it was 1.2. We would have said DNE, and DNE would be a perfectly acceptable answer. I would not mark that wrong if you put that. But what's a better description? Infinity, right? Because from the left and from the right, aren't we increasing without bound both directions? And so I think infinity would be a better answer. But DNE is certainly correct because infinity is not a real number. Question, Christine?
Would you say infinity or would you say negative?
So we're only looking at the graph on the left.
Okay.
We'll get to the graph on the right here in a second. So as you approach 1 from the right, so that would be from here, you can see that we're still increasing without bound. Yeah. Any other questions? Okay, let's take a look at the other one. And I'll ask kind of the similar questions we did before. So with the other graph on the right, if I said limit as x goes to 1 from the left, what would you say to that?
Positive.
Yeah, so from the left would be this side, and I agree, we're increasing without bound. Positive infinity. And then what if we do the exact same thing except from the right? Negative infinity. That's because we're talking about this branch right here, decreasing without bound. And then finally, if I ask the same question I did before, just the limit as x goes to 1, Say again? That's definitely D and E. This would be D and E for a different reason though, right? It wouldn't be because the answer is infinity. It's because
They approach both.
two different behaviors. Yeah, approaching two different values. In fact, couldn't you say that the behaviors could not possibly be any more different? From the left, it's positive infinity. From the right, it's negative infinity. You can't find any two things that are further apart than those. They're not even numbers, right?
It's no further than 10 in infinity.
That's true. That's true. Or 20 trillion in infinity, right? Yeah. But from a conceptual standpoint, you think, hey, they're even going further and further apart, I guess. So, Jonathan, your point is well taken. Okay. I like it. No, I like that you're thinking. That's good. That's good. Okay. So, we're going to take just a little bit of an aside here as we kind of process this. Remember that these limits are pretty much always associated with a vertical asymptote. And so I thought we would take just a second and kind of discuss that. So take a look at that next section there. I worded this question specifically because it doesn't always work out the way that we think it will. What can cause a vertical asymptote when we got one of these rational functions? Dividing by zero. So yeah, I'll just put it like this. Dividing by zero. Zero in the denominator will cause that to happen. So you realize that sometimes a zero in the denominator will actually cause just a hole or one of those removable discontinuities, kind of depending on what the top is, right? But at least looking at division by zero, that's going to at least lead you to think maybe there's a vertical asymptote there. So at least consider that. So why don't you guys try numbers 1 and 2, looking for any and all vertical asymptotes. Okay? Give it a shot. Macy, for number 1, what'd you do?
I did f of negative 1 because then it
Okay, f of negative 1 equals what?
1 over 0.
And then what's your conclusion?
There's a vertical asymptote
At where?
negative 1.
This would be where WebAssign is going to be a pain in your backside. If WebAssign did ask for a vertical asymptote and you just put negative 1, you realize it'll mark it wrong? Even though negative 1 is kind of the correct number, it's going to want x equals, right? Is a vertical asymptote. So I do have a question for you, though, Macy. You've definitely identified the vertical asymptote. There's no doubt. But what if the number in the denominator is not so convenient? Like obviously negative 1, right? It's going to cause the denominator to be 0. What could you do? What if the denominator was less pretty? What would be a way that you could still solve for a vertical asymptote or zeros in the denominator if it wasn't so obvious? I agree, you're right. I'm just thinking what would be a method that would work whether the numbers are pretty or not so pretty? Any suggestions? Say again?
Just set it equal to 0.
Yeah, that's what I'm looking for. So yeah, if you just did 2 parentheses x plus 1 equals 0, and then just solve that for x, you'd get the same answer, obviously, as you did. That would maybe be a little bit more reliable way, just because it'll work whether the numbers are nice or not. Nice work. Okay, and then what about number 2? McKenna, what'd you get for the vertical asymptotes there?
I got positive and negative 3.
And once again, we're going to want to put x equals, especially with WebAssign, they're going to want x equals on something like that. So, okay, awesome. We good? Break out your calculators. We're going to do our final 3 questions here in this section and we'll be done. So we'll just totally use the calculators for these. I do have one question I want to change though, so let me get to that.